Jnanam Paramam Dheyam. Knowledge is supreme.
So, we have proved 4 implies 5, now 5 implies 1, this is the longest implication, because you remember what is 5, 5 is a Noetherian local and the maximal ideal is non-zero and principal, and from this we want to cook up a valuation, discrete valuation. So, we need to define a discrete valuation. So, we have given the maximal ideal is non-zero and principal. So, M is generated by T, let us say, and T is non-zero. This is what we have given, and from here we want to define a discrete valuation. So, from here first note that every element of A non-zero, every non-zero element of A can be uniquely written as U T power n, where U is a unit in A and n is some natural number, unique. That means this U and n are uniquely determined by that element. Okay, why that? So, start with a non-zero element A. So, let 0 not equal to A be an element in A. Now, what do we know? We know that by Krull's intersection theorem, A T power n, n in n, this intersection is 0. This is by Krull's intersection theorem, because A is Noetherian local and M is the maximal ideal generated by T. Okay, so, therefore, this non-zero element, it belongs to, there will exist. So, there exists an n in n such that A will belong to A power A times T power n and not the next one, and it does not belong to A T power n plus 1. It cannot belong to all the powers. So, you stop where it belong, where it does not belong, and just one step before that. So, now because of this A, you can write it as some U T power n. Now, I want to check that this U is a unit and this n is unique, and okay, this is what we want to check, where U is in A. Now, note that this U cannot be in, U cannot belong to AT, because if it is a multiple of T, then this A will be a next multiple of this one. So, because of this, U cannot be this. So, that means U is not in the maximal ideal. So, that means because we are in a local case, so that means U belongs to the units, U is a unit in A. Okay, now, if I have two different expression, uniqueness. Now, if I can write this as some W times T power n, where W is a unit and M is natural number, then because of this you shift. So, that will imply, because of this equality, that will imply, let us assume n and m, I want to prove n equal to m. So, let us assume that n is bigger equal to m, assume this. So, then when you do this, then what do we get? You cancel power of t. So, u t power n minus m will be equal to w. which is a unit. So, this cannot happen unless n equal to m, because if n is not m, then it is in the maximum ideal. So, n is equal to m, and once n equal to m, this is, and hence u equal to w. So, we have proved that every non-zero element of the ring A is uniquely in the form u times t power n for some unique natural number n. So, we can define V. Okay, so before I define V, note that now the quotient field K, any element of the quotient, any non-zero element of the quotient field, I can write in the form some u unit in A cross unit in A, and now I can allow negative powers also. So, that is every element x in K non-zero, I can write uniquely in the form x equal to u t power n, where u is in unit in A and n is integer. Because any element of K is some element of A divided by some element of A, and then you club the units together and the powers also together, and you will have to allow negative powers. So, every element we can write like that. Now, we can define V on A minus 0 obviously to Z. You define any non-zero element x going to this unique power n. So, that is V of A, V of x, this is n, it makes sense, and let 0 go to infinity. So, I get a valuation, this is a discrete valuation, and we have to check that this satisfy those three properties of the valuation, namely it's this is a group homomorphism and V of x plus y is bigger or equal to, but those are easy to verify. Verify that V is a discrete valuation on K, and also it is clear the valuation ring of this RV is precisely A, because RV is precisely those elements of the quotient field where value is bigger or equal to 0, but that is precisely means the elements are in A. So, that means, so that is A is a DVR. So, this proves the theorem completely. Okay, now I want to deduce some corollaries. Okay. So, I just want to make one remark in about the proof. So, in the just last implication, 5 implies one implication, 5 implies one implication. The choice of T, see in 5 it was given that the maximal ideal is principal. So, the choice of T. So, note that the choice, a generator of M is called a uniformizing parameter for A or V. There is a choice for a generator, because one may choose some other generator to be unit multiple of the given T, and then but the valuation will be the same. Okay, so that valuation V is called a canonical discrete valuation. V is called the canonical discrete valuation of K. Okay, so let us deduce some corollaries. So, corollary 1, okay, so let A equal to RV be a DVR. And M be the maximal ideal. So, values are positive and K is the quotient field of A. T is the uniformizing parameter. So, usually this is the data one gives, RV, that is V maximum ideal uniformizing parameter. Okay, then 1, every element of K. So, this is like a summary of many implication. Every non element of K is uniquely written in the form U T power n, where n is Vx. So, every element x Vx and U is a unit in A. Sorry. For non-zero element. Two, every ideal, every non-zero ideal A in A is a unique power of M. So, that is A is M power n. Actually, it is in fact A is Ax, if A is Ax, then A is M power Vx. We know A is principal, A is the principal ideal. So, this is a power of value of that x, generator of A. Third, ideals in A, this set is a totally ordered set. Under inclusion, by inclusion. Totally ordered means it is ordered, that means reflexive, transitive, antisymmetric relation, and it is comparable, two elements are comparable. So, 4, an element x in K is a uniformizing parameter, for A if and only if value of that element is x. Value is x is 1 then obviously it is in maximal ideal, and obviously it has to be generator. If it is not a generator, it will be in a M square and so on. Okay, so this corollary is easy to, this is a summary of the implications what we have done in earlier theorem, but this is nice to memorize things. Most important is ideals is a totally ordered set. Okay, next corollary, let A be a normal domain and K is the quotient field of A, then so this corollary will give examples of discrete valuation rings. So, one, if I localize A localized at P, and obviously we know for a discrete valuation ring dimension is 1. So, we localize at a height 1 prime, so that this ring has a dimension 1. So, is a DVR for every height 1 prime ideal. P in A. So, for example, when you take a polynomial ring over a field, then we know it is a normal domain, and if you take a prime ideal of height 1 there and localize there, it will be a DVR. Or if you take a regular local ring of arbitrary dimension and height 1 prime there, the localization will be DVR because it is dimension 1, and we have proved regular implies normal. Incidentally, regular implies normal. I have rewritten the proof in the corrected another proof today, which is much simpler. Do not have to go through the graded ring. Okay, second part. If I have a non-zero element in K, if 0 not equal to F is in K, the quotient field, then note here, I am going to use the notation which will come from 1. Once this is a DVR, then it will have a discrete valuation, and that discrete valuation is usually denoted by V suffix P. This is the discrete valuation. Corresponding to this AP. So, if F is non-zero element in K, and if then Vp of this F is 0 for almost all height 1 primes, height 1 prime ideals, P contained in A, and where this Vp is, where Vp is the discrete valuation, Vp is the discrete valuation corresponding to P. This is a generalization of that fundamental theorem of arithmetic. Okay, proof. Okay, so one, we want to prove it is a DVR. So, by our characterization we can prove either of the one of the 5. So, the easiest is to note that it is a local domain and also Noetherian, because A was Noetherian, A is normal, so Noetherian, and dimension is 1. So, the fifth condition, A Noetherian local and the maximal ideal is non-zero and principal. No, yes, height 1. So dimension is 1, not the 5 but 3 is better. 3 says A local, normal and dimension is 1. So local, AP is local, and because A is normal, A localization P is normal, and the dimension is 1 because height is 1 we are considering. So 1 is clearly AP is local, normal and dimension is 1, AP which is height P which is 1. So by 3 implies 1 of the theorem, AP is DVR. Okay, second part, what do you want to show? We want to show that for each f non-zero, only finitely many VPF finitely many values are non-zero. Okay, so start with a non-zero element f. Actually, start first with an element in A, and P prime ideal of height 1. Then because f is in A, f is also in A localized P, and therefore Vp of f is non-negative. But I want to show that only for, if it is 0, what happens when it is non-zero. So therefore Vp of f is non-zero if and only if Vp of f is positive. That is, if and only if f belongs to the maximal ideal of AP, which is PAP. But that is if and only if f belongs to P. So how many P's it can belong to f, that is what we have to analyze. So if f belongs to P and height of P is 1, that only mean that will mean that then P will be associated to A by AF. But we know that the number of associated prime ideals are finitely many. So therefore only finitely many P's will have this property. So that proves that, so this is finite set. So therefore the assertion follows. So therefore Vp of f is non-zero only for finitely many P's. P with height P1. Now we are done only in A, but now take arbitrary element in the field K. So that will look like f by g in K and non-zero. But then what is Vp of f over g? Take any P with height 1. Then this will be equal to Vpa, Vpf minus Vpg. This is because it is a group homomorphism. And the same, this is non-zero for finitely many, this is non-zero for finitely many, and at most f over g will be non-zero for finitely many P's.